Hi, this is Captain Steve Tarrant with another video lecture from NS301 Stability here at Maine Maritime Academy. So in this problem, we're going to be looking at, we're going to be constructing statical stability curves. And in particular, we're going to be doing this problem, which states, using the Stability Data Reference Book, determine the danger angle of permanent list if you have a vessel with a kg of 25 feet and the forward and aft drafts given. In fact, we're actually going to answer more than just that one question about permanent list. We're going to answer all these questions as well. What is the remaining GM? What is the maximum GZ? What is the angle of deck edge immersion, which coincides with the maximum GZ? What's the angle of dangerous list? That was the question asked over on the left. And at what angle of heel is the vanishing point? What is the range of stability? So to start this problem, we start with our drafts. So we're going to take our forward draft, aft draft, and we are going to average those to, we got to get the mean draft. So that's 1506. With that, we're going to go into our hydrostatic tables. So if we have a mean draft of 15.6, and that makes, we slide over here to our saltwater curve, and we have a displacement of 7,500. Now, depending how we graph later, we may want this km as well, which we can pluck now. It's about 24.4. Okay, so now we know our draft is 7,500 tons. Let's go to our cross curves. This is the next page in the blue book. So we enter, this is GZ, or riding arm in feet, and on the x-axis is our displacement, and then these curves in here are for various angles of inclination. 15 degrees, 90, 30, 75, 60, and 45. So we're going to draw a line there for our displacement, and then we'll just slide up till we intersect these curves, and we pluck our GZs right off the y-axis. So the next thing we're going to want to do now is take this data and put it into a table or put it into some kind of format where we can start to do a calculation. Because if you'll notice here in these cross curves, this is for a kg assumed of 20 feet. But our problem, our ship has a kg of 25 feet, which means these GZ values are not valid. We have to adjust them from 20 to 25. And to do that, we're going to do that by multiplying, well, we're going to have to do it by a function of the sine of theta, which we're going to look at here in just a moment. So this is the table we're going to actually construct. Starts off over here with the various angles of inclination, which are match up with these angles here on the cross curve. And we're going to do a sine function on all those angles. So sine of 0 is 0, sine of 15.26, so on and so forth. By the way, those values are given to you right up here. Right? The cosine values and the sine values are given to you on the cross curves. Now here's the thing that is kind of interesting. This is where we're actually correcting for our change in the center of gravity. This thing says is that the change of center of gravity is going to be a function of the kg assumed, which was 20 in this case, and the kg actual, which is 25. 20 came from the cross curve, okay? Which means it's going to be -5. Now, you might say to yourself, why are we on -5? Why wouldn't we just do them the other way? 25 minus 20, get a +5. Well, here's the reason, okay? It's really a bookkeeping reason, and it's also, it makes sense in a way. Because we are going to be, if you raise the center of gravity, you're going to be decreasing the riding arm. We're going to see that in just a minute. Which means that we're going to be, our correction should decrease the riding arm. Okay? Which means we will be subtracting it. So we're going to come to all these things in just a minute, but that is why this is kg assumed minus kg actual. So that we end up with a negative value because we're going to be decreasing our riding arm by raising our center of gravity. Let's look at why we're using this sine function. Okay, so this comes right out of your book. It's figure 7.6. This g right here represents the kg for 20 feet. This g here represents the kg for 25 feet. So this is what the curves are made off of, and this is our actual kg. So you can see that there is a difference. G rose by 5 feet, 20 minus, or 25 minus 20. But we set it up over here the other way, 20 minus 25, so we get that negative value. Well, why are we doing that? Look here. At a kg of 20 feet, GZ is represented by this line. But at a kg of 25 feet, GZ is represented by this line, which is shorter than this one. It's shorter than that one by a distance of this. This is how much GZ is going to decrease between a kg of 20 and a kg of 25. And that correction is going to be a function of this angle theta, the sine of theta, which is opposite over hypotenuse, which becomes GZ equals GG sine theta. So that is, okay, because this is the GZ correction right here is going to be equal to GG times sine of theta. And that's what this is right here. And you'll see that GZ is getting smaller in this case as the center of gravity goes up. And that is reflected in these values. We're going to decrease our GZ by 1.29 feet, by 2.5 feet here, simply by taking our change in the center of gravity and multiplying it by the sine of theta. So this column here came from this column times this column. Okay? So 0.5 times -5 is 2.5, so on and so forth. All right? Now we're ready to plot if we want. This, by the way, these are the actual values of GZ for, this says GZ tabular. That's really for a GZ of, for a kg of 20 feet. These GZ values are the ones plucked directly from the cross curves. So what do we have now? We have our angles of inclination. We did a sine function on all those angles. We have our change in the center of gravity, which is a negative value, okay, so that we end up with a negative GZ, okay, which we're, and then this is the actual GZ that we had for 20 feet. That was a lot. Let's plot. So we're going to go to this. Now, to plot, we're going to plot these values and these values. Okay? That's how we're going to plot the first time. All right? So here we go. First thing we want to do is we want to do the first 10 degrees of the plot. Well, yeah. So what we need to do is we need to get our value of GM. So Km was 27.4, which we got from here, and our Kg was 25. Okay. So what are we plotting right now? We're going to plot a curve for. We're going to start this plot by plotting a curve for a Kg of 20, which is the values we got right here. So in that case, if Kg was 20, then GM would be 7.4. So I'm going to slide up this. This is 1 radian, and the interesting thing is that at 1 radian, the ratio of GM to GZ is 1:1. Simply stated, at 1 radian, I can plot GM on the same scale that I've got GZ on over here. So I can just plot that at 7.4. So that's what this line is. I've extended this up to 7.4, and I plotted this dotted line. The first 10 degrees of angle will follow that line linearly because that's your initial stability. Now, the next thing we're going to do is we're going to plot these values. Okay, so 2.1 at 15, 4.7 at 30, 6.6 at 60, and so on. That's these data points here. And now we'll smooth those out with a curve. This represents the stability curve, the statical stability curve for this condition. Displacement of 7,500 tons, kg of 20 feet. Okay? But we know our vessel is not at a kg of 20 feet. We're at a kg of 25 feet. So we have to now make a correction. Well, this is the correction. These numbers represent how much GZ will be decreased for each angle. So all we have to do now is take these numbers and plot them here. So 15 degrees, we're going to decrease by 1.29. 30 degrees will decrease by 2.5. So here's 1.29, here's 2.5. We can plot all those. Okay? And when we do that, we can get a nice smooth curve there. Now, here's the interesting thing. A minute ago, we plotted this curve off of this zero baseline. Okay. Now we're going to plot our corrections, and we're also going to plot them from here. But the thing that happens now is that you need to realize is that at this point, this no longer exists. All the area underneath this red correction curve goes away because that was valid for a kg of 20, but now we're correcting for a kg of 25. That's what all this was. So in a way, in a very real way, this now becomes zero line. This was our zero line, but now this is our zero line because all this went away. And this is what is remaining of our stability for a vessel with a kg of 25 feet and a displacement of 7,500 tons. So now, if this line represents 0, I can actually measure along from this to here. This now is the curve for 25 feet off of this new baseline. All right, now that doesn't make sense to you. You're going to have to listen to that again and perhaps go into Chapter 7 and read up on that little section in Chapter 7. Okay? But we're now ready to answer all of these questions. So let's do it. What is the remaining GM? Well, at 1 radian, the ratio of GM to GZ is 1:1, which means we can read our GM directly off here at this 1 radian, 57.3 degrees line. And we get this GZ here, which if you measure that over here is a little bit more than 2 feet. Well, what's the maximum GZ? Well, you take your dividers and you start measuring distances from the red line to the blue line, and eventually you're going to find the greatest distance, and that should be right around here. And if you measure that, that should be something around 3. Okay, and we're going to I'll give you the actual numbers here in just a minute. What is the angle of deck edge immersion? Well, deck edge immersion occurs at the maximum GZ. So that means that deck edge immersion is going to happen somewhere down here. I don't know, what's that, like 50-ish, 49, something like that. What is the angle of dangerous list? By definition, the angle of dangerous list, or the angle of or the danger angle for permanent list, okay? Angle of dangerous list, where's my cursor? There it is. Angle of dangerous list, danger angle for permanent list, they're really the same thing. It's defined as half of the angle of deck edge immersion. So if this is 50, it should be, right over here. So that would be about 25 or so, or 20. Okay, actually, I put that in the wrong place. I can see I made a little error in my PowerPoint. If this angle is 50, this should be at 25. It should be just a little bit further over. Okay? And at what angle is the vanishing point? The vanishing point is when GZ equals 0 again. Okay? So if this is my 0 line, that is right here where my curve comes back down and touches my 0 line. That means that my vanishing point is here, somewhere around 80 degrees. Okay? What is my range of stability? It's going to be from where it goes to positive, from 0 back to 0, which is about 0 to 80 degrees. All right? So this is what we end up with. All right? And by the way, I made a little mistake in reading this. This angle here should be really 50, which makes this one 25. So there's a little error there, but you can deal with that, okay? All right. Well, we've done all that. That's great. It turns out, though, that perhaps there's a simpler way of doing all this. Wouldn't it be nice to be able to just plot the final curve off of the original baseline? Okay? And kind of skip plotting this curve and split plotting this curve, and just plot whatever is this area back down here. Well, we can do that. We can do that by having one more column in our table. And that column is called GZ final. Okay? So the GZ final, which in this case is for a vessel with a kg of 25 feet, is going to equal the GZ assumed, which was from the cross curves at 20 feet, plus the GZ correction. That's these guys. So when I take the GZ assumed, that's these numbers, and I add the GZ correction, which is a negative number, in this case, I'm going to get these values. So I could actually just take this number, subtract this number, and I would get that same column of values. You see, for instance, this right here is like 2.1 minus, oh yeah, look at that. 2.1 minus 1.3 is 0.8. So I can get these numbers right off this graph, and but if I just when I was making this table at this point, if I instead of starting plotting here, I just waited until I had these numbers by subtracting or by doing this function GZ assumed plus GZ correction, I could just skip these two curves and just plot the final curve. That would be a little less work, wouldn't it? The reason I've gone through this whole process is I want you to show you where the final curve comes from. It comes from these two curves, okay? But now we're going to get rid of those, and we're just going to plot the final one. So here we go. 0 degrees, 0. That's right here. And here's 15 degrees, 0.8, 2.2 at 30, okay, so on and so forth. And you'll notice here that 90 is at -2. Interesting thing to note, right here, you can see there's interesting things. GZ max is going to happen somewhere around 45 degrees. And the vanishing point should happen someplace a little bit more than 75 degrees. We can see that right from the table. Well, we can also see that right here. Okay? So this is our final curve. All right? This is our final curve. It represents the same information as this. This one is using this as our baseline, but by doing the subtraction of the two, we move these data points back down to the original baseline. Okay? And now we're ready to answer all these questions again. So there is our GM, which again, look, 2.3. Oh, 2.3. That's the same number from before. Of course it is, because it's the same information. Where's the angle of maximum GZ? Well, okay, right here at 45. There it is right there, 45. Okay? What is our angle of deck edge immersion? That is going to coincide with that, 45. And that is right there. What is the angle of dangerous list? Well, it's going to be half of 45, which is 22.5. All right. And at what angle of heel is the vanishing point? Well, vanishing point is going to happen at 0, which if that's 75 and that's 90, that should make that about 80, which makes that 79. All right. There is that. And what is the range of stability? Well, that goes from 0 to 79, which is there. Okay. So as it turns out, now that this curve is done, you remember previously I said there was a mistake. It looks like the mistake I made earlier was I stuck the GZ at the wrong angle. I think I stuck it at 50 degrees earlier. I should have stuck it at 45. So this is the valid curve. These numbers are all correct. I just made a little boo-boo on my PowerPoint earlier. Well, I hope that made some sense to you. You should probably go ahead and watch this again or certain parts again. And how to do this is actually in your book in Chapter 7. And it starts in Chapter 7 on page, looks like about page 134. All right. And it goes from page 134 through about page 144. So it's about 10 pages. All right. Good luck.